Okay, guys, so we are on this section that deals with more descriptive chemistry. So the first thing we're looking at is metals. So what is a metal? Let me remind you of what a metal is. Right, so is a metal an element in which the atoms possess one, two, or three valence electrons? Is this what we say about metals? Okay, so I like this table to compare metals and non-metals. You all will tell me if you agree. All these things should be a bit of review for you, right? So you will find it sounding familiar because you kind of did it when we were bonding and structure there, right? Are metals good conductors of electricity and heat? Are these things that you know? So metal is an element that has one, two, or three valence electrons, right? Are they good conductors of electricity and heat? Yes, how many of you are aware of that? Right. Would you expect a non-metal to be a good conductor of electricity? Are you all seeing this table clearly? All right, good. So you will write down some properties of metals. So metals, good conductors of electricity and heat, right? High melting points, you'll agree with that? Are they hard and strong? Are they malleable and ductile? We did this long time, right? Are they shiny? Do they have a shiny appearance? Do they make a sound on impact? Are they sonorous? Yes? Okay. Right. So tell me when you have these properties listed, just to remind you. And do you recall that metals do metallic bonding? Right. What is that again? Is that where the valence electrons becomes delocalized into sea of mobile electrons? So this is what happens with the metals. Their valence electrons become delocalized and they enter into a sea of mobile electrons. And it is this because of this sea of mobile electrons that allows them to be good conductors of electricity. Is this okay? And because they're closely packed, that allows them to be good conductors of heat. Okay, I will pause a minute to help get you started with writing for me. All right, so metallic bonding, again, is where the it's a type of bonding that is described as intra because it doesn't take place between two or more elements. It's within the metal, right? To stabilize it somewhat. So I'm not saying it will be entirely stable. I'm just saying it's stabilized enough to exist. So what is it? This is where the metal cations, remember metals have one, two, or three valence electrons. So these valence electrons would become delocalized, right? Again, they enter into a sea of mobile electrons. So this is the sea of mobile electrons. And what we see, the metals become cations. So the strong electrostatic forces of attraction between the metal cations and the sea of mobile electrons holds the structure together? Let me see lattice, right? I like to see lattice. Some metallic lattice. So it's held together by that attractions. Could you guys tell me, since we're reviewing metallic bonding, you did quite in Form 4, early Form 4. Tell me what is responsible for the conduction of electricity. Yes, Joel, what is responsible for the conduction of electricity? Is it the sea of mobile electrons? Very good. Which is delocalized? So can they move when a voltage is applied? Yeah, guys. So is it sorry about that? Is it the sea of mobile electrons that holds the structure together, right? So it's the delocalized electrons that is responsible for the conduction of electricity because they can move when a voltage is applied. Is that true? Right. So you know about conduction of electricity. I'm not going to worry about that. Do you know then why metals are good conductors of heat? Do you know why metals are good conductors of heat? Is it because the atoms are packed very close together so that when we heat one end of the solid, if we apply heat here, this one is going to vibrate. And then if this vibrating strongly, it's going to cause the other atoms to vibrate. So heat can quickly travel from the hot to the colder regions of the metal because of that vibrations, because of the fact that they are packed closely together. Are you okay with conduction of heat? Let me know. If you go back in your Form 4 notes, you'll see it. Are you guys okay with conduction of heat? Let me know. Right. Are you also okay that metals have high melting points? Help me explain that one. Why metals have high melting points? And look at here. Is it because of the strong electrostatic forces? Very good. Whenever you're to talk melting points, boiling points, you must use the word forces, right? Here we have strong electrostatic forces. Strong meaning a lot of energy is required to break it, right? Nice. Good. So you know that. I'm not worrying about that again. What about metals having high density? Why are metals dense? How come metals are dense? What does density mean? Density is equal to mass over volume. Very good. So that has to do with how closely packed they are. So the more closely packed they are, if something is packed closely, that means more mass per unit volume, which means a high density. Is that true? Very good. So that has to deal with closeness again, right? Next, why are metals shiny? Is it because of how closely packed they are as well? Yes or no? Since they pack so closely, when light hits it, it is simply reflected off the surface, giving the appearance of being shiny. It is due to reflection of light. So the light is simply being reflected rather than going through or passing through the material. Is this okay? So shininess also deals with how closely packed the atoms are. Is that okay with you guys? Right. And we could ratch this easy, right? All properties of metals. Either you explain it in terms of the delocalized electrons or how closely packed the atoms are. Is that okay with you? Right. Can I continue from here? Right. This is revision. Right. So I cannot spend more time on this. We need to move on. Right. So good. Why did I put this? Why did I put this? Too often I see students mixing up a physical property and a chemical property. So I've decided here to separate for you. If they ask for physical properties, that deals with what? Melting point, boiling point, malleability, ductility, conduction of electricity. Whereas chemical properties is how they react, right? What they combined with. Is this okay? So take down for me some physical properties, which you have already, but just categorize it for me right now. So physical properties of metals, you can write any of those, right? Good conductors of heat, high melting boiling points. Whereas the chemical properties is that metals form positively charged ions or cations. They form metal oxides when they react with oxygen. They are reducing agents. You just did redox, right? It forms metal hydroxides, which are basic. Metals react with acids to form hydrogen gas and a salt. All of these things are things that you did when we did acids, bases, salts, right? So you will find a lot of overlap between this section and section A. That's why section A was done before this, right? Tell me when you have a note here. Us doing this question last week when we reviewed, I told you about this and the observations, etc. I'd see you. Could you remind me of the back now? If you know metals are reducing agents, what is the reducing agent here? Which one is going to be the reducing agent? And these were the oxidation numbers. Which one? It was the zinc, because the zinc itself is being what? Oxidized. Is that true? Right, so you can prove it if they ask you this. Metals are reducing agents. Write an equation to illustrate your answer. And you can write this redox reaction, right? So how many of you remember that from last week? The question with the zinc and the copper sulfate, where it turned pink. You remember that? The zinc strip turned pink. Anyhow, you all would look over. Next, the reactivity series now. Right, our famous reactivity series. This is where I wanted to get at today, right? So what is the reactivity series? So it's a list of metals, actually, common metals. Okay, guys, I don't know what's going on today. Right, guys. So it's a list of common metals. Hope you all were writing. And their order of reactivity, right? Is this okay? Do you all remember the reactivity series? When I did it with you in acids, bases, and salts? Remind me of them. Do you know it? Potassium, sodium, calcium, magnesium, aluminum, zinc, iron, lead. Hydrogen is placed for reference, right? Copper, let me write symbols. Copper and silver. How many of you know the reactivity series out offhand? And I gave you a way of remembering them with knowledge and commitment. So, y'all remember that? All right, fine. You've remembered how you know it. So it's a list of common metals. Nice. And using this reactivity series, I can work out the reactivity of any metal in the periodic table. I'll tell you more about it in a little while. So take down point number 1. Point number 2 is displacement, meaning a more reactive metal. Will displace a less reactive one from solution. I think you know number 3. The more reactive the metal, the more stable is its compound. All right, here what? Let me give you a chance to write. Point number 4 is important. And point number 5 also important. Okay, tell me when you all have it. All right, so we're ready here to explain the reactivity series. Right, so one more time, what is our reactivity series? So it is a list of common metals, because if you think about it, you know all of these metals: potassium, sodium, right? Calcium, magnesium, aluminum, zinc, iron, lead. Hydrogen is a non-metal. It is placed here for reference. And we have copper and silver. So what we say is that the metals at the top are more reactive. So reactivity increases this way. And using the reactivity series, tell me if you guys agree, using these metals alone, the reactivity series, together with your knowledge of periodicity, you can gauge reactivity of all metals on a periodic table. Okay, let's say that, right? Okay, think about this. If I ask you to put the metal rubidium in the periodic table, in the reactivity series, where will you put it? You are tasked with putting rubidium. I want you to check your periodic table. You have a periodic table. And tell me where rubidium is in a periodic table. Where is rubidium in a periodic table? Is it below where? Is it in group 1? Here what? I just sent you a periodic table. Where is rubidium? It is below potassium. Very good. What do you know about the reactivity of a metal when we did periodicity, when we did group 2, group 7? Do you recall that the reactivity of a metal increases down the period? Increases down the group? Sorry, reactivity increases down a group of metals. Who remembers this line in purple? Purple here. And for the non-metals, the reactivity increases up the period. We met these 2 points when we did group 2, and you met this one when we did group 7. Okay, so tell me then, where to put rubidium if you have to inject it in the periodic table? where to put rubidium if you are asked to put it in the reactivity series, sorry. Very good. You will put rubidium there. Am I making sense to you? Okay. How many of you understand that using this list of common metals and your knowledge of periodicity, you can gauge the reactivity of metals on the periodic table, all metals? Let me know in the chat if I've made that point clear to you right now. I will pause here for 1 minute to let you write on whatever you need to, because this is important. I'm pausing. Y'all agree with that? All right. Can I continue then? So we're going again. What was the second point? What does the second point deal with? Hold on, let me just erase everything. I'll just write it back. Second point, a metal will react with a compound. Right, that's displacement there, right? So I'm just putting it back for you. Right. Did you all write on the reactivity series, the list? So I won't have to write it back. So tell me now, again, is a more reactive metal going to displace a less reactive metal? Do you agree that this will happen? Where am I pen now writing? Zinc. Famous displacement reaction is this one. You'll see this over and over. This is, if we doing displacement, this is most famous, right? Why did this reaction happen? Is it because that zinc is more reactive than copper? How many of you agree? And displaces it from a solution of its salt. Do you agree with point number one? Let me ask you something that, will this happen if I use solid copper sulfate? Will it work that way? If this is a solid and this is a solid, will they be able to displace? No displacement here. Displacement happens in what? Solution. Is this clear? Now this could happen if you heat it, then you could melt this, right? If this is heated and this melts, then it could displace, right? Tell me if it's okay. Can work if two solids are heated, but not with two solids alone. Do you agree with me? How many of you agree here that are more reactive metals? So you agree with point number one, right? Point number two is this. I can look at it like this. Zinc sulfate is more stable than CuSO4 and therefore more likely to be formed Can I say that too? Is zinc sulfate going to be more stable than copper sulfate because zinc sulfate has a more reactive metal than copper sulfate? The more reactive the metal, the more stable the compound. Do you remember me saying that to you? Recall, the more reactive the metal, the more stable is its compound. Do you guys agree with these 2 points? So, one more time, will this reaction happen? Aqueous, solid. Will this reaction happen, guys? What do you say to this? Is number 1 possible? Is number 2 possible? Okay, tell me your answers in the chat. Will number 1 happen? Will likely happen? Very good. Yes, so number 1 is feasible, energetically feasible, meaning it will happen or should happen. Number 2 is not feasible. You can show it like that, right? Because why? Copper is not more reactive than zinc. Is this okay with you guys? All right, so tell me, in terms of the compounds, zinc sulfate versus MgSO4, which is more stable? Which compound is more stable, zinc sulfate or magnesium sulfate? Answers in the chat. Which compound is more stable, zinc sulfate or magnesium sulfate? Very good. MgSO4 is more stable than ZnSO4 as why? Is made of a what? More reactive metal. Is this okay? Could you guys tell me if I'm fine on the board, if you are okay with this? Guys, is this things we did already? Did I not talk through these things already with you sometime? So for sure, by now you must know it, huh? Because this is a section that really deals with it. Are you okay with this? And which compound is more likely to be formed? Zinc sulfate or magnesium sulfate? Therefore, MgSO4 is more likely to be produced or formed. Is that okay too? The more stable something is, the more likely it's going to exist. Let me know if you agree with these things. All right, can I take this off? Is this in your books? How many of you have this in your books? You will tell me when then. Fill in the blank for me. So this is the displacement I'm looking at. Magnesium reacting with zinc sulfate, forming MgSO4, add zinc solid. Aqueous, because displacement must take place in solution. Right, so this is a displacement. And why does it happen? Because magnesium is more reactive than zinc. All right, I'm not writing that yet. You will help me here. Magnesium metal is done MgSO4, therefore is done you need a blank there. Okay. One, give me all the words here. What word is number one? Magnesium metal is what? Than zinc. More, right? More what? Very good. Reactive. Nice. When you're talking about the metals alone, you talk reactivity. All right, good. You know that. Therefore, than zinc metal. That true? Magnesium metal is more reactive than zinc metal. Is that true so far? Therefore, MgSO4 is, what word am I looking for here? 4. More, and what's the word at 5? Stable. Nice. When you're talking about the metal alone, you're comparing reactivity. When we're talking about the compounds, these two, what word applies to these two? Stability. So the more reactive the metal will form a more stable compound. Is that point clear for you guys? Let me know. Can you let me know if you agree with me? All right, can I take this off then? Yes, guys, Leah, can I take this off? Are you okay here? All right. This is my reactivity series. Again, fed up writing it for you, but I'll keep writing it so you'll see it all the time. Lead, hydrogen is a non-metal. It is the reference point. Copper and silver. Right. One more time. Which compound is more stable? CuSO4 or CaSO4? Is more stable. Which one is more stable? 1 or 2? Put answers to me in the chat. Good. Anybody else can put answers to me in the chat? Which is more stable? Copper sulfate or calcium sulfate? Number 2. CaSO4. Very good. Is more stable. Is that clear, guys? Why calcium sulfate is more stable? As it is formed from a what? From a more reactive metal. Nice. If a compound was made with a more reactive metal, that means the metal wants to react, right? It's going to form a more stable compound. Do you understand me, everyone? All right. Y'all sure you're okay? Right. So good. I'm done with that point about reactivity. So that was point number 2. We're on number 3. Well, I kind of did those two in one, right? The more reactive the metal, the more stable its compound is, meaning it doesn't break down easily and easier to form. How many of you good with points 2 and 3? You good with points 2 and 3? All right, tell me now. Next, extracting a metal. Extracting a metal. So, think about this now. Let's see. Aluminum is extracted from the earth from its ore. Those of you who know, bauxite. Right, so aluminum is extracted from the ore, which is bauxite, Al2O3 plus impurities. Right, an iron is extracted. I'll define one thing after for you, right? From hematite. TITE, which is iron 3 oxide. Right. So this is how we get aluminum. We'd use bauxite and make aluminum. And then we take iron oxide, hematite, and make iron. Okay. Could you guys tell me which compound is more stable, Al2O3 or Fe2O3? How many of you agree, based on what I just told you, that Al2O3 is more stable than Fe2O3? Therefore, a more powerful method is needed to extract aluminum compared to iron. Do you agree with this point? It's kind of spin off from the previous point. If something forms a more stable compound, is it harder to extract it? Would it be harder to break it up? Let me know. Yes, guys? Okay, you're right. I think you are writing. So, the more reactive a metal, will it form a more stable compound? And if it forms a more stable compound, is it harder to extract the metal from the earth? Would it be harder? Yes, it will. Right? We'll require a more powerful method of extracting it. We'll deal with that, more about that when you meet it, right? We're going to meet all of these things in some greater detail, right? Next, the less reactive metal, the less likely it forms compounds. Do you agree with this point? Do you ever hear them say that they're mining for gold? Like we can actually dig up the earth and get gold? Because it's found as gold in the earth? Tell me something. Gold and silver. Silver is not reactive. Would silver form stable compounds? Answers in the chat. No. So if it doesn't form stable compounds, will you expect it to exist in its native form in the earth? Write this word for me. So in the earth, okay, let me ask you. In the earth, will you expect to dig up the earth and get aluminum metal? Guys? Will you expect aluminum to be found as aluminum in the earth? No. Aluminum is found in bauxite. I just told you, right? Bauxite, which contains alumina, Al2O3, plus impurities. So, alumina, how come aluminum is not found as, why can't we dig up the earth and get aluminum? Is it too reactive a metal to exist alone? Let me know. Yes, right? But gold and silver, are they reactive metals or not? They're not. So will you expect it to be found in its native form? Right. Did you write down the word native? All right. Guys, are you okay with that? All right. Next, will you expect magnesium to be found in the Earth's crust? Or are you expecting magnesium to be found combined in the Earth's crust? I'll expect it to be combined, right? I will not expect it to be in its native form. Very good, right? So I think you got 0.5 across, 0.6 now. How did we come up with that reactivity series now? I don't understand how we get the reactivity series. Often in past paper questions, they give you this: magnesium, zinc, and copper. And here's the past paper question, how it reads, right? Describe an experiment. You'll write it down to deduce the order of reactivity. Any ideas? I'm giving you a minute to write this down. Some of you might even get this as a planning and design. I'm sure some school would do this. Right. How can you do an experiment to determine the order of reactivity? All right, let me give you one idea and we'll see if we can get another. We can possibly do displacement. Let's tell you. Number one, add a strip of magnesium, maybe about a 2 centimeter long strip, to 5 cm cubes of zinc sulfate and 1 molar. Always write concentration in a test tube. And observe. 2. Then you're going to do the same thing. Add a strip of magnesium to 5 cm cubes of copper sulfate in a test tube. And observe. How many of you agree with those two? Then you're going to take the zinc strip and do the same thing with magnesium sulfate and copper sulfate. You all agree? Repeat steps 1 and 2 with zinc and MgSO4 and CuSO4. And step 4, repeat steps 1 and 2 with copper strip and MgSO4 and ZnSO4. Does this make sense to you guys? A planning and design, you'll get expected results, right? So expected results. And tell me if you'll agree. So I have magnesium metal, zinc metal, and copper. And I'm adding it to magnesium sulfate, zinc sulfate, and copper sulfate. But I won't add magnesium to magnesium sulfate. A metal won't displace. Right, I'll see nothing there. That don't make sense to do that. Well, will I get a reaction here? Will I get a reaction here? No visible reaction. We won't do this. Zinc to zinc sulfate. Zinc to copper sulfate, we will get a reaction there. Copper, no visible. Will copper displace zinc? No. Will copper and copper sulfate? No visible reaction. Okay, what do y'all see happening here? Which is the most reactive metal on the board if this were the results? It'd be magnesium. Why? Is magnesium displacing zinc from zinc sulfate and copper from copper sulfate? So is magnesium more reactive? Look at it. Is magnesium more reactive than zinc and copper? So far. So least to most, I'll put magnesium. Okay. Which metal is least reactive? Did copper displace magnesium from magnesium sulfate? No. Did it displace zinc from zinc sulfate? So is copper least reactive? How many of you agree that experiment would lead us to this results? And we can use displacement to deduce the order of reactivity. How many of you okay with this? Let me know how many of you are able to describe an experiment to compare the reactivity of metals. Let me give you a next possible experiment. Is this in your books, by the way? I did not ask you. What about this experiment? Tell me if you'll agree with this one now. So again, same problem. You are given 3 metals, magnesium, copper, and zinc, and you are asked to decide which is most reactive. You could have done this. 1. You can do this reaction with acid. Right, so 1, add a 2 cm strip of magnesium to a test tube or beaker. All right, let me put a volume to, let's use 5 again. 5 cm cubes of a 1 molar HCl in a test tube. Two, then you can do the same thing. Observe. Add a 2 cm strip of zinc to 5 cm cube of a 1 molar HCl in a test tube and observe. Right, 3. Repeat. Step 1 with copper in place of magnesium. I don't want to write over all of that, right? How many of us okay with this method too? Or you could have done this. Set up the following apparatus. You could have done this. We do reads here. We did reads already, right? Syringe. Strip of metal. And how much? About 40 cm cube of a 1 molar HCl. Use a stopwatch and record the volume of gas at every minute interval, right? Repeat for all metals. I've done this too. If I want it to be more detailed, the more reactive metal will be the fastest rate of reaction. How many of you prefer this method? Right, let's give you guys some expected results. How I expect you to write results. Right, so for the first one, with your magnesium, zinc, and copper in acid, right, what do you say? Tell me what you think if we just watching these and deciding which is most reactive based on this. What would what do you think would be the observation with magnesium? Very vigorous effervescence. Can I say that? Or rapid effervescence? Don't want to say vigorous. Let me see. Hmm. Right, what do you guys say? Tell me if you agree with magnesium. Rapid effervescence, you'll agree? The magnesium strip quickly disappeared, right, forming a colorless solution. Guys, you all agree with me? Because we're forming magnesium chloride and hydrogen. How many of you agree there? And for the zinc, you can write steady effervescence, right? The zinc took a longer time to completely react. Can I say that? Is that showing comparison between the two metals, guys? Oh, guys, you agree or you don't agree? And what do you think for copper? No. Can I say no visible reaction? Yeah? No bubbles observed. Who agrees with me? Take it down. That'd be for the first experiment where we just watching it. So this would have been the experiment if we're not measuring rates, because we can actually watch it and tell that magnesium is going to be most reactive because they're producing a lot of bubbles, right? The effervescence will be rapid and the magnesium strip will quickly disappear. We can actually see it. Is this okay? The one with the rates is more scientific though, right? If we were doing measuring rates, you would plot a graph, let's tell you. So experiment 2, which would be the rates experiment, you'd plot a graph of volume versus time, and your experiment should, your results should go like this. We're doing time in minutes, right? Right, which one would be the magnesium? I don't want to curve it yet. Which one would be the copper? Which one would be the zinc? Tell me which one would be which one. 1, 2, and 3. Which one would be which one? Which metal would produce results like 1? Let me fix the pink line, huh? Right, 1 could be your magnesium. Is that okay? And 2 could be which one? The zinc. And 3 could be copper. We won't really get a gas. Tell me if you're okay with that. One is the most reactive metal. And 3, least reactive. Guys, you're not saying anything. Are you okay with this? No. Tell me when you'll have it. You like method 1, right? But sometimes in situations, do you have to do method 2? Like if the metal's really close in reactivity and you cannot tell with your eyes? You tell me. If 3 metals are really close in reactivity, would metal 1 work? Do you think? I don't feel so. You'll agree? Right, so you'll do method 2 for that, right? Anyhow, let's continue. Reactions of metals. Head up reactions of metals now. And the first one is reaction with air or oxygen. And before you write the note, I want you to write some equations for me. 1, sodium and oxygen. Tell me what you'll get and balance it. 2, Mg and oxygen. And 3, Al and oxygen. Right, metals react with oxygen, that's number 1. Write these 3 equations and then we'll write the note. All right, how many of you were able to write equations for these? Did you get Na2O? Yeah, and you put solid, right? Because the oxides are solids, they do have no aqueous, no liquid water to dissolve it, right? So you have to form it as a solid. We don't have no liquid water here. And you put 4 to balance. Yeah, that right? What did you get? 4 to balance? Tell me what you get. Did you get this? Right. What about the second equation with MgO? You form MgO, it must be a solid. Did you get this equation? You can't put aqueous even though it's soluble because it have no liquid water in any of these. It'll be formed as a solid. Right, aluminum, Al2O3, right? What you get here for this one? 4, 3, 2. Right. How many of you got these 3 equations? Very good. Right. Are you okay with the equations? When a metal reacts with oxygen, you'll form the metal oxide and put them as a solid because there's no water to dissolve them. Right? The sodium is a solid, it has no water there. The oxygen is a gas, it have no water there. Is this okay? Right, let's take this note now. Read it as you write it. Right, metals will react with air to form a metal oxide. These metal oxides are either basic oxides or amphoteric. I'll talk about amphoteric after. We did that when we did a type of oxides. The more reactive metals like sodium and potassium will burn in air. Right? Sodium and potassium will burn rapidly in air. Right? There's some sodium and potassium. Catches fire in air. because it's so reactive. It must be stored under oil. Write that down for me. I'm just summarizing here, guys, right? Sodium, potassium, right? Magnesium will tarnish, wrap quickly in air, and if heated, burns with a bright, blinded light. Bright, white light. Is this okay, guys? How many of you got that? All the others tarnishes slowly in air, right? If you powder it, of course it'll burn faster because in the powdered form will have a higher rate, right? And these metals shows little tarnishing in air. How many of you agree? Guys, do you agree with this? Yes or no? Tell me if it makes sense. Are you all okay with reactivity with oxygen? Right. One more thing before I close. Could you tell me this? Why does aluminum, so this is a piece of aluminum, why does it seem unreactive? Gosh, oh yeah, my pen going through. Why does it seem unreactive? Aluminum. How come? Because aluminum metal usually would have a layer of aluminum oxide formed around it. Right? Which is non-porous. And prevents further reaction RXN with oxygen. Is this okay? Guys, are we okay here with this? So if they ask why the aluminum metal not looking like it burning in air, it is because it already has a layer of the oxide on its surface and it's non-porous, right? And it prevents any further reaction. Do you guys agree with me? Do you have this? There are older questions that ask why aluminum seems unreactive, and this is the answer. It is a fairly reactive metal, so by the time you get it, it would already have a layer of aluminum oxide. Already has a layer of Al2O3. as it is reactive. Let me know if this is okay, guys.